And we're up. There's a couple of interesting pictures there that I wanted to talk about real briefly before we move on. On 263, one of those pictures has something kind of like this. How would you all define this region right here in terms of concavity? Yeah, it's concave up, and then over here, concave down, and this point right here we discussed was an inflection point. But then the next picture has something kind of like this, where you've got a concave down here. Do they call this an inflection point?
No.
No. Why not?
Because no change in concavity occurs.
Yeah, the concavity doesn't change. Okay. Just wanted to kind of make sure we're good on that. Also, the difference between increasing and concave up. Okay? Clearly, this is increasing and concave up. Question is, can you have increasing and concave down? Can you have something increasing but have it be concave down? Yeah, what would it look like, Rajal? Something kind of like that. Notice the function's still increasing, but it's concave down. And just in the same way, you could have decreasing and concave down, but you could have decreasing and concave up. So just be very clear. Increasing, decreasing are something completely different than concavity. So that was kind of an interesting phenomenon. There are three tests that we deal with. One of them with sort of like with relative maximum, stuff like that, and absolute maximum. One of them was just to give them formal names and make it very clear. We talked about the candidates test for absolute extrema. That was, you find the critical points, you find the endpoints, and then you literally just make a table with those and f of x, and you figure out who's the highest and who's the lowest. That's called the candidates test. I give when I taught AP, we really make a big deal about naming these tests and kind of going through a whole rigmarole, but I'm fine with y'all seeing this and moving on. There's something that we already did. I didn't specifically give it a name. I didn't call it by its name, but we did it, and this was the first derivative test for relative extrema. And that was back in, might have been slightly before I had to read. Oh, you ought to read that. That was on page 260. And it was, if f prime changes sign, at C, and f prime of C equals 0, then you're looking at a relative minimum or a relative maximum. If the derivative goes from positive to negative or negative to positive at that point, and that the derivative at that point is 0, that means you've got a tangent line, or a horizontal tangent line. That was the first derivative test, and you kind of took care of that. There's one more, and this is called the second derivative test. You took notes on it. And without me actually telling it to you, see if you can make some sort of conclusion. Don't glance at it just quite yet. What if I said this? If the second derivative, I'll give you a specific point. If the second derivative at C is positive, think about what that means. Don't say it, just think it. And f prime of c equals 0. Then c is what? Second derivative is positive at that point, and the first derivative is 0. Then what is c? You want to make a guess?
Minimum.
What's that?
Minimum.
It's a relative minimum. How do you know that?
Because I read it.
What does second derivative greater than 0 mean?
Oh, that it's concave up.
It's concave up. So you're concave up. What does this mean?
That it's going to be like flat.
That it has a horizontal tangent line. So if you've got something that's concave up and has a horizontal tangent line, there's only one place where there's a horizontal tangent line. That is at the relative minimum. Does that make sense? In the same way, we could say if the second derivative is negative, so that means it's concave down, so we can see if we have less than 0, and the derivative at that point is 0. You get a situation you're concave down, and that's your tangent line is horizontal, then you must be looking at a relative max. Alright? This gutter. No, what do you need? Oh, I am teaching a lecture actually. That's okay, alright. Monday. So this is someone just wanted to talk. Just tell him to call back next week. Thanks. And get where he is from. So even better. Email's great too. Yeah, great. Yeah, thank you. People want to talk. Okay, it's called the second derivative test. You're like, oh, what's it called the second derivative test? Well, because basically, if you say the first derivative is equal to 0, okay, then let's look at the second. Then we know it's either relative maximum or relative minimum, okay. The second derivative test says figure out what the second derivative is at that point. If it's positive, you're looking at a concave up relative minimum. If the second derivative is negative, you're looking at concave down, so it's relative maximum. So the second derivative is kind of able to tell you whether it's a relative minimum or relative maximum. Does that make sense? In contrast, the first derivative test says, okay, find a situation where your derivative equals 0, okay? Then use the first derivative, plug in some values to the left of it, plug in some values to the right of it, and that will tell you whether you're looking at a relative max or relative min. Because if it's positive, negative, or negative, positive, then that'll tell you. Does that make sense? So that's the difference between the first derivative test and the second derivative test. The first derivative test, anyway, I don't need to say it. I don't need to repeat that the fourth time. So anyway, all right, that's it for that section. We've done some problems. I'm ready to move on, and we can apply some of this stuff. Okay. Let's turn in our books over there to 4.5, and let's look there and at our notes that you kind of summarize the major points there. I'll read to you the first paragraph, and then y'all can tell me some of the interesting things that you noticed. So the title is Optimization Problems. The theme of this section is optimization, a topic arising in many disciplines that rely on mathematics. A structural engineer may seek the dimensions of a beam that maximize strength for a specified cost. A packaging designer may seek the dimensions of a container that maximize the volume of the container for a given surface area. Airline strategists need to find the best allocation of airliners among several hubs to maximize fuel costs and maximize passenger miles. In all these examples, The challenge is to find an efficient way to carry out a task, where efficient could mean the least expensive, or the most profitable, the least time-consuming, or, as you will see, many other measures. Okay? So we're trying to optimize. We're trying to get the biggest bang for our buck. We're trying to make the most money, or have something cost the least, or get the most area or volume, or any of those things. So what are some things that y'all wrote down for your notes on 4.5?
There's a constraint.
Okay, there's a constraint. So there's always something sort of limiting you.
Mm-hmm.
Is that what you mean?
Mm-hmm.
Okay. What else?
Then you have the function you want to optimize.
Okay. Did they give a name for that function?
Yeah, objective function.
The objective function. Okay. So the quantity that you want to maximize or minimize is called the objective function. Okay. So if we were trying to let's say we wanted to maximize our profit, then what we would want is we would want to have a function profit as it depends on some other stuff. Okay? If we wanted to minimize the volume of something, then we would have V equals some other stuff, and we would want to obviously figure out what numbers need to go here in order for it to be the absolute smallest. In these cases, the profit and the volume are dependent variables. And then over here, you have one or more, independent variables. You have all your other things that go into that, okay? Now, what we are learning right now is calculus of a single variable, okay? And we know functions that look like this. P of x equals, sine of x squared times, I don't know, x cubed over square root of x. I don't know. We can solve problems when we have one independent variable. Okay, we can take the derivative of this all day long, right? So the problem is that when you're dealing with situations like airline passengers, or volumes of boxes, or things that the company is making, it doesn't just depend on one variable. It depends on multiple variables, and for that you need to do it right. For the really more complicated situations, you need multivariable calculus. Okay, but before you can handle multivariable calculus, you have to be able to handle one single variable calculus, which is why we're learning this. And in our problem setup, sometimes we're going to have x's and maybe h's and maybe an r or something like that. And in those situations, okay, we're like, well, I can't, if this is a variable and this is a variable, this is a variable, I can't take, multiple variables. What we're going to have to do is to turn those other variables, like the h's and the r's, all into x's somehow. So find a relationship. Find, for instance, that we found out that h is equal to, maybe it's 1/3 x, and r is equal to x squared. And then plug those in so that we have the profit completely dependent on x. Then we can do all of our calculus stuff, okay? But what we're looking at, the type of problems that we're doing, we're looking at word problems, okay? And being able to translate what that situation is into an equation, and then somehow through other mathematical processes turn these multiple variables into just one variable, and then we can apply our calculus stuff, okay? And this is called the objective function. What are some other things that y'all that y'all noticed? Or that you wrote down? Or that you had a question on?
There's guidelines, optimizations.
Yes, I'm looking on page 282. Rigel, read those first two guidelines for optimization problems.
The first one is read the problem carefully, identify the variables, and organize the given information with a picture. The second one is identify the objective function, the function to be optimized. Write it in terms of the variables of the problem.
Okay, so write it in terms of the variables of the problem. Sounds good. James, go ahead and read number 3 to us.
Identify the constraints, write them in terms of the variables of the problem.
Okay, so figure out what your limitations are, what your constraints are. Keep going, James. Number 4.
Use the constraints to eliminate all but one independent variable of the objective function.
That's what I just kind of walked through us verbally. I'll read what he said. He said, use the constraints to eliminate all but one independent variable of the objective function. So that's why I said we need to find ways of turning these other variables into just one independent variable. Okay? Ivan, number 5.
With the objective function expressed in terms of a single variable, find the interval of interest for that variable.
Okay. So we need to be realistic and say, okay, this x, or whatever happens to be, it really can't be negative because x represents the number of people that are working here or whatever. And it doesn't make any sense to have negative people. Okay, we don't employ no ghosts. All right. So or anything. I don't know what a negative person would be, but that seems kind of weird. Anyway, we can't we can't employ more than 200 people because the fire marshal says there's only the most amount of people that you can have in this building is 200 people or something like that, or in these rooms or whatever. So you have to identify what are the realistic values of this variable. James, number 6.
Use methods of calculus to find the absolute maximum or minimum value of the objective function on the interval of interest. If necessary, check the endpoints.
Okay. So let's just be honest here. What if I gave you a problem that looked like this? The profit as a function of x, where x is the number of people, is kind of go off that one. Sine of x squared up by itself. Sine squared x times x cubed times the square root of x plus 1. And I want you to find, that's probably a terrible question, but just for whatever this is, find the maximum profit that you can make. And when you find that maximum amount of profit that you can make, tell me how many people we need to employ. And we'll fire some people if we need to, and we'll hire some people if we need to. This is going to maximize our profit. Does that make sense? Okay? So find the maximum profit you can make and the x value that gets you there. And you had never taken calculus before. How would you do that? How would you find the maximum profit? Ivan?
The value that gives you the highest P.
Yeah. How would you figure out that the value that gives you the highest P?
Just plug it in.
Plug it in and?
Comparing.
Okay, what do you mean by plug? Okay. Kind of deviating from the intro I was kind of looking for. When you say plug it into
The equation.
plug it. Well, what value would you plug
X.
in? Which x?
Every X.
Every x. So maybe graph it
Mm-hmm.
with the calculator or other graphing utility, right? So I graph it, and then what? I'm trying to find the maximum profit. This is no calculus needed. Help us out, James. I put it into a graph and it looks like this. This is the profit.
Find the maximum.
Yeah, that's my whole point. Thank you, Harley, for bringing us down to earth. Yeah, it's not that hard, okay?